I may get back in time to see the second half, but I'm not sure.
Oh. Admin stuff is admin stuff, and one cannot.
Just realizing that next week is the 4th of July week, and a lot of people are disappearing for some time, so some things need to get taken care of.
No. It makes sense. It makes sense. Okay.
All right. So our second lecture of the morning will be Alejandra to continue on AdS CFT. So please go ahead.
Thank you. Here we are again, third time. So I guess I failed at one thing, because I said that I was going to be democratic about how much I do about AdS and how much I do about AdS CFT. But I left you guys in a cliffhanger, and I don't want to give the wrong impression about features of the gravitational path integral. And you also didn't let me go into my crisis mode. So we'll spend probably, I guess, the first 30 minutes of this lecture wrapping up what we left unfinished from the previous one. So I wrote down here on the board basically the last key equations, which basically it took us forever to get from here to here. And then there was also lots of questions on going from here to this expression. But this is basically where we left it. I wanted to discuss how would you compute the path integral in pure AdS3 gravity, so gravity without any additional degrees of freedom, with torus boundary conditions, and with the assumption. So yeah, maybe what did I assume? What were basic things that I assumed that you were like making uncomfortable and disapproval faces of things that I was assuming? What did I assume? Saddle point, okay, good. What else? Nothing else? That's it? Done?
C is large, I guess.
Smooth, yes. I have smooth, and then you were saying? Yeah, in particular, at the minimum, yeah, so let's put C large. If you want to be generous, you can say C bigger than 1, which is basically reflected in this equation that I'm writing the vacuum character as if the only null states are L minus 1 and L bar minus 1. But in correlation with the saddle point approximation, yes, you're thinking that the central charge is very large. So yes. And I think that's it. I don't know. I don't remember. Did I assume something else? Am I forgetting another assumption? Each of these were, well, at least the first two were quite controversial, if my memory does not betray me. But OK, in any case, that's where our assumptions. OK, So in my naive head, these are pretty okay assumptions. And the references that I listed on the Google Drive, you can see the details of evaluating the sum. I am not going to do it. This takes a little while, okay? And you can ask Shuheng for details about how to do it if you're interested, because he has a beautiful paper on how to compute the sum. And you can also read the Maloney-Witten paper where it's discussed how to do the sum. The sum diverges formally. It's an infinite sum. You have infinite integers C and D that you have to sum over, and the exponential that you get in the sum goes to 1 as C and D go to infinity. So you have to be careful, but this is something that people have thought about carefully. And there's an answer that you get. There's at least 2 different regularization methods that have been applied, and they give the same conclusions that I will tell you. Okay, so that what happens, so you can evaluate this. So you can regulate and evaluate. And to illustrate a little bit what happens, this is not the whole answer, but just to show you a bit what happens. And as you do this, what you get here, you get a term, basically, again, the vacuum contribution, which is fine. And then you get something that looks like this. And then you will get some coefficient that I'm too lazy to write because it's not going to be super important. And then you get higher order terms like this. And then you get even more stuff. And here y is the imaginary part of tau. And I'm now ready to go into crisis mode. Why am I? So today I'm not laughing. I'm not smiling. I'm not excited. I'm jet lagged still. What looks wrong about that answer? The -6 looks terrible. Terrible. Okay. Negative coefficients. That's not the only one. That was the one that was noticed and the first time the computation was done, but there's actually infinitely many negative coefficients that lie when the states are close to the extremal bound. So that one is just, I'm just writing those terms, but there's actually a whole set of accommodation points that have negative coefficients. So ideally, so in my dreams, what I wanted, what I hoped, as someone that likes unitary and so the hope here was that this, you could interpret it as a trace over a Hilbert space of this form, given that it's a partition function on the torus. And given that I don't have any fermions, there's no -1 to the f here or anything to be said. In particular, you should have, at the minimum, interpret this as a sum over degeneracies v to the minus beta h in some way. So this was the hope. If you get negative coefficients, good luck. It's like, no, not going to happen. And then the second problem is this power behavior in y. So this is basically beta, right? Divided by 2 pi. And as this formula reflects, if you want to have basically an integral expression for those degeneracies, you should only have like exponential powers of beta. And so this power law, basically behavior, tells you that you are in the presence of a continuous spectrum. Now, last night we were talking about this. It depends a little bit on who you are and how you feel, and maybe if it's Monday or if it's Friday, I don't know. How terribly depressed you get about either of these conclusions. When the results first came out, I think people were equally concerned about both. They were pretty terrible. Nowadays, the second one, it's interpreted differently. So it's taken a different take, that basically this continuous spectrum could be accounted by not demanding that you had a trace of a single Hilbert space, but that you were doing an ensemble averages of CFTs of Hilbert spaces, and that ensemble average, it's what accounts for this continuous spectrum. This is one point of view, one way how you can think about that. I don't know what is average over. I don't know what that measure is, but that's the claim. Okay, that's why people nowadays, if you hear talks, they don't think that this is so terrible. So it will be the claim that pure AdS gravity is not dual to a single CFT, but a collection of CFTs defined somehow. The negative coefficient one is something that, at least in this context, can be addressed somewhat. But in either, and I'll tell you a little bit about how we can address either of these two crises, so possible solutions at this stage. To these pathologies are the following. And I do welcome, this list is not going to be exhaustive, because I think we're learning more and more every day as we learn more and more about AdS-CFT. So this is what I know about how people can address this problem. So as I told you, just to write it down, so the continuous spectrum could be understood averaging over CFTs, okay? I do want to stress could, because it's not like it has been proven very rigorously. There's evidence towards it. There's beautiful work towards it, but this is one approach. Now, the negativity can be cured if you add, there's various ways, there's not, and we believe that there's more than one way, but the negativity can be cured in a very minimal way if you wish, just from the point of view of like, you want to get rid of these negative signs, and you want to get rid of all of them, not just the -6, but every single negative sign, and so the negativity can be cured if one adds, a finite number okay? This is one way how you can cure it. It's not the only way, but one way that you can cure it is basically you tell me, there's more saddle points inside of that answer, okay? And so that's one possibility. Now there's another possibility And instead you modify a bit what the theory of gravity is that you have. So if you consider something, so here we were looking at just Einstein-Hilbert gravity, and where we found basically this Hilbert space spanned by 2 copies of Virasoro. There's ways how you can modify a bit the theory of gravity such that the phase space is just 1 copy of Virasoro. Okay, and that's what goes under the name of chiral gravity, which in the gravitational context, this is it goes also under the name of topological massive gravity at mu times L equal to 1. And for this theory, you have consistent Brown-Hinel boundary conditions, and the phase space is just, so let me just say it, the phase space is 1 copy of Virasoro. And if you redo that computation, then that computation basically doesn't have like the absolute value. Okay, so it's just basically a computation where the partition function of chiral gravity just depends on tau. It doesn't depend on tau bar. So that's what it means for it to be chiral. So then you would also sum over images in the same fashion of just the vacuum character, which just will be this same object, but without the Q bar dependence. And this basically has, you also have to regulate the sum. It's again a Poincare series that you have to regulate. But the result here is that all the coefficients are positive and discrete. It's basically a polynomial of the J function, if you know what the J function is. If you don't know what the J function is, it doesn't matter, but it's basically discrete. And the only ambiguity is the constant term, the term q to the 0 is the only term that is subtle and what might depend on how you regulate the sum. So this is one fix, at least from the point of view of negativity and continuous spectrum.
What sacred principles the regulators might violate?
The what?
Do the regulators use to keep the sum violating the sacred principles?
Okay, I was asked if the regulators violate any sacred principles. I'm not sure what your religion is. In the religion of physics, one of the methods is quite natural, is zeta function regularization. So you force the sum to converge by introducing an S that damps basically the coefficients inside of the sum. I think in my head that falls within. Is that sacred? Yeah. So that's the one that is like the most intuitive, the one that I understand the best. And again, I have used it in other contexts in QFT, and that one still gives this problem. So yeah, the other ones are more mathematical, more fancy, above my pay grade, and I don't know how to translate them into a nice like QFT. Like myself, not the people that use them. They do understand them and how to explain them. But the zeta function regularization is the one that is very natural. And I think, I don't know, I was just happy with that one. And then I was very impressed that people also tried to do it different ways just to see, well, you do try to do it different ways given that you're getting a negative result just to check that it doesn't. There in the front? Yes?
So how do we see that this zeta function regularization is also consistent with modular invariance? Like for instance, if you look at the
so that's where you have to be careful. So no, it's not obvious, but you still have a sum over images. So if you wish. So the trick, yeah. So the sum over images, in some sense, it is assuring to you that you will be complying with modular invariance. So it's always a Poincare series from that point of view. But so I think this was not the worry, or at least I was not worried about that introducing the zeta function. Like it changes the weight, and so then you might be worried, oh, what happens when you go back to S equal to 0 and things like that. But the sum over integers is always, the sum over the images, that's what makes the object modular invariant. So it's like an Einstein series. Like you just grab something and you sum over the images of it, and it's going to be modular invariant.
So very naively speaking, the second term doesn't seem to be modular invariant.
I'm not writing everything, so that's why there's lots of dots everywhere. So this is not like the answer. So you're not supposed to see that it's modular invariant from what I wrote. The terms that I wrote, I cherry-picked some terms from the Maloney-Witten paper just to illustrate my crisis. But of course, this answer is not like reflecting that. Like it's just a part. It's like if I just write down the vacuum contribution, yes, of course, it doesn't look modular invariant. But you know that you have the sum over primaries, and then it's going to be modular invariant. So it was just I wanted to draw the sad face. That was. I could have just said it in words, but I thought writing an equation might be helpful. There. Yeah. Here, if you want it to be invariant, so it has to be a multiple of 24.
The second comment is that I guess we don't actually think those chiral gravity exists.
I was going to comment. So the drawback of this third point. So there's a very nice paper using this topological modular forms that actually show. So what happens here, if you do this sum, and you can interpret it then as a you can see that it looks like a trace of some q to the L0 minus c over 24. But the spectrum basically has a big gap, which is the gap between AdS and the first black hole. The first primary basically shows up when the first black hole shows up. And so the spectrum here is compatible with what you would have called an extremal CFT. And extremal CFTs, they do exist for low values of the central charge. For c equal to 24, they exist. 72, I think there's a few examples. So you can count like a few examples of values of the central charge where you have these extremal theories. But what has been shown in recent years, I think I wrote down, I didn't write down the year. Probably was 2 or 3 years ago when Dupay and Yingxuan Lin last year? I don't know. OK. I'll put the references in the Google Drive, and you can read the paper about the existence of these extremal CFTs. I wrote the name of the authors, but I forgot to write down the year. 2021. 2 years ago. December. OK. So these things, in correlation to the condition, I wanted the central charge to be very large, although you can write down this polynomial that has all these properties, these do not exist.
In what sense?
That there's not like so the CFT is not just defined by its spectrum. You also have to define its LPEs and so forth, and so it's believed to not exist from that perspective, that it will comply with the other axioms of a CFT. Now, I was asking you to explain to me what a topological modular form was and how do they prove it. I failed, so don't ask me. I did not understand how they proved it. I just know they're very solid results and basically.
To be fair, they didn't prove anything. They used the proof by a mathematician and showed that the extremal violated.
Yeah, so I'm being indeed. So they used some mathematics to show that mathematics basically implied that these theories don't exist. Chiral theories do exist. It's just that the condition of extremality is quite strong. It puts a lot of constraints on the spectrum. So I don't want to say that chiral CFTs don't exist. It's just that the special class of extremal CFTs don't exist. So there, off you go. Terrible news again. More crises. Now, the fourth comment and last one, and this is the comment, like just to be a little bit uplifting, is that another thing that you can do. So here we gave up in these 2 points. We have been modifying the theory. So we made some tweaks to pure gravity to see if we could get some mileage. The fourth thing that you can do is say, well, what if I take C to be small, and in particular to take C to be less than 1? And given that we have heard so much about CFTs with C less than 1, I thought I wasn't going to mention this, but I was inspired by the other lecturers to mention it, given that it goes well with the theme of the other topics. And so that you might consider looking at theories that have C less than 1. And defining, basically asking the question, so this more broadly asks the questions, which CFTs that are unitary and therefore make me happy can you rewrite their partition function? So usually we write their partition function in terms of characters. When is it possible to rewrite this object as a sum over images? Oh, let me write the same notation. So here I'm putting the identity as the vacuum configuration. You might ask the question, when is that within the realm of possibilities? Now, if C is less than 1, this is it's an easier question to ask because the elements of SL2C are finite. You have finite number of primaries, and modular transformations just rotate the primaries among each other. And so then this is basically a question about matrices. Okay? So when can you rewrite this in this way? And so we asked this question many years ago, and there's actually only 2 cases where you can do this. So within the family of minimal models, you might have discovered the Ising model by asking this question in a way. So the 2 cases where you can do this is when C is equal to 1/2 and when C is equal to 7/10, which is the tricritical. So this is Ising. And what you find basically, so the sum over images in this case, sorry, here I meant to put the gamma in there. The sum over images in this case gives you 8 times the partition function of the Ising model, and the sum over images in this case gives you 48. These 2 theories, from the point of view of what defines an extremal CFT, are also the only minimal models that are extremal, meaning that the first primary has a gap of C/12 in terms of its energy. Okay, so it's kind of a cute coincidence that the only 2 minimal models that are extremal from the point of view of their spectrum, it does happen as well that you can write down their partition function as a sum over images of the group. But this also doesn't buy me much because C is less than 1, and then I don't know what semi-classical gravity is. But as an exercise of asking which CFTs it makes sense to recast their partition functions in this way, at least, okay, I know of 2 examples where it happens. Yes?
So for higher C, when you do this sum, you get linear combinations of different modular invariant partitions.
Yeah, so there's
coefficient.
Yeah, so the most common occurrence, so it depends on the value of C. The thing is that for various values of C, you have to contrast the space of physical theories versus the space of, or the basis of modular forms that you have. And so if the space of modular forms, if the dimensionality of that space is equal to the number of physical theories in the AdE classification, then what happens in this exercise is that you get combinations of theories. So you do the sum over images, and it looks like the AA plus the AD plus the DA, whatever combination. If you have an E there floating around, it comes in there. But there's also specific values of the central charge where there is a modular invariant form, but it's not physical. Its spectrum is not attached to one of the ADE models. We actually learned that from Terry Gannon, because DiFrancesco does not tell you this. The Big Yellow Book does not mention this. So we learned that from him because we were confused that there were values of the central charge where we were getting negative coefficients. And we're like, wait, we have a mistake because everything should be a physical theory if it complies with modular invariance. But no, there's actually values of the central charge for which you have the number of modular forms that you can construct is not exactly equal to the number of like minimum models at that value of the central charge. So you can also get negative numbers here. And these are the only two theories for which there's a unique also theory. So at c equal to 1/2 and c equal to 7/10, there's just one theory. So we were doomed to success.
Why do we, for other C, you get some linear
Yeah.
combinations of C's?
So then it looks more like this conclusion in some sense that.
Well, but also already for C equals to 1/2, you can say it's 8 copies of the IC.
I know, yeah. Yeah, so this 8 was, yeah, maybe if you want, you can interpret it like this. But at least, yeah, so. But we could also have said, well, who knows how you're supposed to define the measure in the gravitational path integral. I don't know. I think that it is a fair point. If you want, you can view this 8 and 48 as like, oh, you averaged like 8 times the Ising model, and then you fall back into this bucket of like of things.
View it as a DAT times the IC.
Yeah, yeah. No, you can definitely, yeah. There's many things that one can interpret, but from a gravitational point of view, I get nervous that besides writing some of these expressions, don't ask me what gravity is when C is less than 1. So I take this as an exercise on modular forms. But okay. But the conclusion that I want to take from here, and this is why I wanted to spend a bit of time. So given the set of possible solutions, my opinion, because you can see like in any of these scenarios, I think, I don't know, what I'm tempted to say is that if you start, so, okay, so what is the lesson here? Now I'm being recorded, and some people don't agree with me in terms of this lesson, but this is, since I'm lecturing, this is my lesson. But I'm just saying it because you might find different opinions. What I learned from this is that everything hints to the fact that pure AdS3 gravity does not have a UV completion. Therefore, we need to find the rules of EFT of an effective field theory description of gravity plus matter such that we have a UV completion. And so in my point of view, the name of the game is understanding what do I need to add here. What are the rules for this such that I can have, when I decide to compute a partition function on the torus, I get a Hilbert space, and then if I do further computations and further checks, I can see this is compatible with a CFT. Okay? So here, by having a UV completion, perhaps I should clarify, it means the dual CFT2 is unitary. Okay? It's a good CFT. That's what I mean by having a UV completion. Yes?
A related question. So, like in these examples where you get the partition function of an extreme CFT, that means that there are other primaries besides the vacuum. So
But they start so from, let me draw a picture. So let's say, yeah.
they're black holes.
Yeah, they will be interpreted as black holes because basically, so here I am at minus C over 12, okay, which is the vacuum in this notation. So delta here, well, this is a chiral theory, so I should put 24. So it's just H. And then basically, so you will have descendants, but then the first primary will hit here. And this is basically, so in the gravitational language, this is where you have BTC, and this is where you have just global AdS3.
So it could have worked.
Yeah, but so yeah. And there's nothing in between besides the descendants, the boundary gravitons. So that's the definition of extremo. But yeah, it was very, this was very promising. But also some people, the fact that so sorry, here K is an integer. A positive integer. There's also a sense in which people were not so clear what was going on here because then maybe because this was always an integer, it's like, oh, what does it mean to take a large C limit? And should the extremal CFTs condense in some way because if they get very close to each other? I don't know, it was a little bit awkward, this integrality condition on them. But okay, you do some exercise, you get this, and then you're like, okay, this looks great. Yeah, I know. but I don't know, it just looked like a bit too good to be true, and so, yeah. But then there was always the debate, and this was a long debate for many years of can we build extremal CFTs with arbitrary large central charges? And there was a lot of evidence against it, but it was still not super tight. But this last paper from 2021, I think in my mind, I'm kind of confident writing, even though I don't know what a topological modular form is. I think I feel very comfortable crossing it out. So yeah. So okay, so this is our lesson.
Alejandra,
Yes.
this might be a very naive question, but are these problems fixed if you consider AdS as being a classification of string or anything?
That's the lore.
Does that depend on what fluxes you're
Well, the lore is that string theory is a UV complete. So I'm being asked if we put this on supergravity or on string theory, if we think that these problems are going to be cured. This is what we believe. We believe it not because this has been computed explicitly and checked that it holds. We believe it because we believe in string theory.
Okay, but that's not proof as such.
Depends on how strongly you believe in. Yeah. But
If we know string theory, that's what we believe.
exactly. Which I think it's also not a great answer to your question. It's an answer that can make you sleep at night, maybe half of the week, if you want. But it's one of the important questions because you want to understand what is special about those CFTs and about those spectra. What is special about that matter? Because the examples that you're presenting to me, basically what they look like from this three-dimensional point of view, it looks like all those fluxes, everything that you had in the extra dimensions, will look from a lower dimensional point of view as a whole tower of matter fields that you're adding to a theory. So what was so special about that combination of matter? Why did I need that matter? What type of matter can I do? Is it all come from string computations? Is there a swampland there? So this is where you become a swamplander. And talk about the landscape of consistent theories. This is basically what I'm asking. What am I allowed to put in here? What are the rules? Does it have to be supersymmetric? Or can I have examples that are not supersymmetric? How do we go about this? Okay? And so when we try to do very simple things, we fail. So now we have to do more complicated things.
in the external CFT spectrum that you wrote down, is the spectrum continuous about CFT?
No, it's discrete. But I'm being, well, it's always, the spectrum is always discrete. I was just like illustrating, like if C is very large, then like the hope is that it looks like continuous because the BTC has continuous mass. But strictly speaking, no, if you read off what the primaries are here, there's a discrete number of primaries for each value of H.
So is H an integer?
Yes. H is going to be an integer. It just comes because of the same reason why C is quantized. So you demand this thing to be invariant under tau going to tau plus 1, and then you're done.
I thought the H comma 0 states is not entirely clear if they are black holes.
That's, the one, so that's right. The green line is like slightly above. Sorry, no, this point is a little bit exactly at 0. You have to be careful.
Yeah, but we have infinitely many such states in the kind of method. So in a sense, it's not really pure.
Yeah. So this is this. I think it depends on how you regulate that statement. Also comes about on how you regulate the sum. That constant term is, it would actually change. There's at least 2 methods that I know that give you a different constant. I don't know if one is better than the other, but one was done by mathematicians. The other one was done by physicists.
But you always have
A constant.
Close to 0 state at one side. And when the CFT is holomorphically factorized, you have infinitely many states of the form H comma 0. And I think all of them, it's not clear if they are
No. Okay, fair enough. But I'm already giving up on this, so I'm deciding to not even interpret this. But yes, it's. So I think also before, like there are some works that try to understand like precisely how to give an interpretation of that 0, 0, and it is subtle. But yeah, I'll move on because I don't think that this will. Even resolving, I don't know what it will mean to resolve that or give it a further interpretation because there's no evidence that you'll get a theory. Okay, so how am I doing on time? Probably terribly because I feel like I'm speaking very slowly. Yes, I'm doing terribly. Okay. Okay, but we're having fun, right? Look, I only used 3 blackboards. Wow, I'm really not writing much. Okay. Okay, so with that in mind, now let's move to CFTs. And in particular, the next thing that will happen to you is basically a discussion of what is a holographic CFT. So what are these CFTs? So I want to reverse this question. So given this obstruction, of course, one way that you can go about is starting adding matter and seeing slowly, like what can you do in order to get your problems resolved. I'll ask the opposite question. So basically, I want to ask the question of what are criteria or conditions on CFTs such that they look like an EFT of gravity plus matter. Okay. Now, answering this question, I don't have a complete answer. So the punchline of this lecture is not like, oh, here you are. These are the definition. These are the criteria, and these are the conditions. No, this is where we're going to like brainstorm, okay? And we're going to be like, what should we be asking? What are these criteria? What are sufficient criteria? What are necessary criteria? What are redundant criteria? How do we go about this? And so the way that we will start doing this is by questioning the successes, okay? So we have hinted, or we have seen that a CFT mimics many features of gravity. So let's list a few, just to see what is going on. So what is the first thing that we have seen? Or no, maybe it doesn't have to be something that we even saw during the lectures. What are things in the CFT, basically controlled by symmetries, that we know that they're going to look the same on the gravitational side? Any thoughts? Can be something that we already computed, or it can be something that we have not computed. Yeah, so I got two answers, and they're similar. So it was the asymptotic symmetry group and the stress tensor being holomorphic and anti-holomorphic. Plus the properties of this, which is basically the statement that we see the Virasoro symmetry. Right? Good. What else? This is all the evidence that we have that AdS3 looked like CFT2, or a CFT2 looks like AdS3. Very good. Isabel. I didn't dwell on it too much, but I also know that you saw it in the first week, but it was basically the Cardy formula. Anything else? That's it. This is all that we do and check in life in AdS CFT. Thank you. Yes. Which ones in particular? Which ones in particular? Sorry, I couldn't hear you. Not quite. Let's think even easier. We'll get to single trace operators tomorrow. But basically, 2-point functions and 3-point functions in a CFT are basically controlled by symmetries. So you're guaranteed that you're going to get them too much, in the same way that the Virasoro symmetry. So I'm not trying to trick you, but I'm just trying to make you question. I want you to think about what are the rules of AdS CFT, okay? So 2-point functions and 3-point functions, because they're controlled by symmetries. And this is also happens in higher dimensions. They're controlled by symmetries, okay? So you're guaranteed success. And then the other thing, maybe a fourth one, but then I do want you to think about more. In 2D CFTs, the other thing that is controlled by symmetries is entanglement entropy of a single interval. That's another observable. We didn't talk about it here, but I know that it's quite trendy and fashionable, so I figure I should. And it's very important. And you also saw how it impacted, for instance, your first week as well with the lectures by Hong Liu, and it's basically the relationship between entanglement entropy and the Ryu-Takanagi formula. In AdS3 CFT2, if you have a single interval, these answers are basically controlled by symmetries. You can view it as a consequence that the correlation functions are also fixed by symmetries. But in a nutshell, you can list more things here, but it's basically anything in the CFT2 where you use modular invariance. Plus the conformal group, roughly speaking. Okay? So there's more things that you can add to that list that you want. These are some of the most famous ones. But what I want to do probably in the last, 10, 15 minutes that I have, is let's revisit a little bit this. So let's be careful, because we know that this was not enough. AdS3 gravity has these properties, but then we're like, OK, but it still doesn't give us a unitary theory. So what are things that we have to keep in mind? So point 1, OK, we know that we don't want any CFT. We want to have CFTs with a central charge that ideally, if the correspondence works, we can match with the Brown-Henao result plus ... in a regime where the central charge is big. So that's also why we're going to forget about the Ising model. I want to focus on conformal field theories that admit a large central charge. This will usually mean that I will have to look at a family of CFTs. Okay, so point number 1, the first one. And then point number 2, and this is where you have to start understanding and appreciating what it meant for these things to match. The second point that we have to now be picky about is basically about regimes of validity. What did it really meant to match these quantities? So let's look at the Cardy formula. The Cardy formula illustrates quite beautifully that we went a little bit too fast, that we're a little bit too quick. So I was not intending to rederive the Cardy formula, and I think given how slowly I'm going, I am not going to rederive it. But I think, are we OK with that? We are OK? OK. But basically, the statement of the Cardy formula as a CFT statement, so let me write it also in the microcanonical ensemble. And I'll only do these statements at finite temperature. I'll turn off the angular potential, but these statements also are true if you turn on the angular potential. The Cardy formula tells you that the density of states at high energies is universally given by this formula, and the relationship between the energy and the temperature of the system is this. Okay? And of course, here, this is not an exact formula. It is an asymptotic formula. There's corrections, ... It's one of the most satisfactory things to derive this formula. It's quite beautiful. So if you have only seen it in lectures but not have done the computations yourself, I strongly recommend it to do it. It's just so nice. It's such a nice derivation to say something so robust about a CFT with so little effort. However, let me rewrite this expression. Oh, sorry, here, t squared. This is important. So t squared here is given by this expression here. And part of the derivation of the Cardy formula, so as you go through this, basically what you're doing is using modular invariance and taking a high temperature limit such that you can project to the vacuum state, right? That's the basic principle of the Cardy derivation. Now, at the same time, I want the central charge to be big. So usually, the Cardy formula, if you don't say anything about the central charge, you always have in mind that this, OK, it doesn't have to be like an ultra big number, but it has to be a big number. But you can see clearly here that this is putting a hierarchy between the energies and the central charge for which this is going to apply. So usually, the statement is that if C is fixed, so if you don't take C to be large, basically, the energies just have to be much bigger than the central charge, OK? Or people will be sloppy, and they will just tell you high energies. It's a very high energy. OK? And it's fine. That's the validity of the correction. If you wanted more details of what happens here, you can approximate this formula and write down the corrections, and this allows you to tell you about the energy, the density of states at lower energies. Now let's compare that with the BT set. So were we expecting that in gravity? So in gravity, we wrote down the entropy of BT set. Like this, right? We agree? Yes? This, in the semi-classical limit, should be a big number, right? This is the validity of the semi-classical regime. Now, this means basically, so we have that. Now, let me translate this statements. I think that's what I want to do here. Yeah. So let me translate these statements now to statements of like how would these conditions look on a gravitational language. Okay, just so that we can compare. So if you translate this to gravity, it's basically telling you, so the energy was the AdS radius times the mass. So it's the mass of the black hole in AdS units. And so this is basically a statement that L times M of the black hole, it's much, much bigger than C. Now C is 3L over G. So this is telling you that the mass of the black hole is much, much bigger than 1 over G. And then you translate that to R plus, and it's telling you that R plus has to be very, very big in AdS units. Okay, that's what the CFT, in terms of like the validity of the Carty regime, just from the CFT, you translate it to gravitational language, it tells you this. But this is not what I want. What I wrote down up there, we wanted this to be valid when R is much, much bigger than G, than the Planck length, when black hole's big in Planck units, not in AdS units necessarily. Of course, the black hole exists. It's not like the black hole will cease to exist, but this is not the same as that. So now let's translate this back to the CFT, and I think, okay, I'll leave you to do this as an exercise, but basically, the exercise here, not very surprising, is that you want this to be true. And basically, or in other words, what you can say is that what you want it to be true is that you wanted R plus to be of the order of L, and then we have that L is much, much bigger than G. So for this regime, roughly speaking, is when the black hole should have large amounts of entropy and should be perfectly fine. Now, this regime basically tells you, from this perspective, that you should have had the formula, the Carty formula, oh, I shouldn't have written it. Let me write it here. So basically, another way maybe to rewrite those things is that the Carty formula should hold for basically up to temperatures of order 1, or when energies are comparable to the central charge, and these two numbers are much, much bigger than 1. Okay? So let's do this also in a different way. So maybe entropy is not the quantity that you feel more comfortable about. Let's look at basically at the free energy, just to further convince you that this is the right regime of gravity. So the free energy, we computed it as well, but I did not draw the phase diagram. So let's draw now draw now the phase diagram. So what I told you was that the value of the action of thermal AdS was this. Therefore, the free energy of thermal AdS is minus C over 12. And for BT set, the free energy is minus pi squared over 3 times C over, I have a typo in my notes, over beta. Over beta squared, okay? That's the free energy that you would associate. This is the free energy that you associate to thermal AdS. This is the free energy that you associate to BT set. So then the question is, okay, as we learn in thermodynamics, basically these two objects are contributing to the same path integral. So the path integral, or the whole partition function, is roughly something like e to the minus beta f. And what I have here are two saddle point contributions. And the question is, for which ranges of the temperature do each of these saddles dominate the ensemble? And so this one will dominate when beta is bigger than 2 pi. This one will dominate when beta is less than 2 pi. So now if we draw a nice picture, so that's why I was writing down temperatures of order 1 then here, because basically then in terms of pictures, if I plot the free energy as a function of temperature, what's happening here, then I have a beautiful point here, which is minus C over 12, for which the free energy is constant. Then I get close to this point where the temperature is 1 over 2 pi, and then I get this behavior. So for temperatures, for low temperatures, here I have thermal AdS3. Oh, I should have used blue for low and red for high, but and then for high temperatures, the BTC looks cooler. You have here the BT set branch. And this point here is the Hawking page transition. So this is the phase diagram in the limit that the central charge goes to infinity. So here I'm taking this strict limit of the central charge going to infinity. The phase diagram that I'm expecting is this one. A CFT that just has the Carty behavior like normal. The free energy of a CFT is continuous. It doesn't have a phase transition generically. Okay? Grab the Ising model. Plot the free energy. It will be a continuous function of the temperature. You're not going to see discontinuities. Okay? And so this is also what's called basically the confined phase. And this one is the deconfined phase. So the reason why I'm drawing this and stressing this is that now becomes the question, not just that we're very happy that we matched the Carty formula, but now the question is, which CFTs have this phase diagram? Because if I only do my Carty formula, this is not going to be true. So what are the classes of conformal field theories that, at a minimum, as a necessary condition, have this phase diagram? Do we know the answer? How much time do I have? 10 minutes? Okay. So what I'll do, I'll just write down the answer. I'll tell you the answer. In 10 minutes, I don't think I can derive the answer. But let's just state it. And then you can see how much, I don't know, how much you object to the statement. So let's do it here. So the question now became, which CFT2s at large C have a Hawking page transition? Okay. This looks like a pretty stringent requirement on the CFT, at least naively. So let's see which CFTs can we characterize from the point of view of the spectrum, the classes of CFTs that comply with this. So the answer to this question was given in a beautiful paper that I'll put as a reference. It's basically the Hartman-Keller-Stoica bound, HKS. And it goes as follows. So the basic idea of that paper, so that they're using, I'm going to do it. They do it for both zero angular potential, and then they also do it for the case where you have angular potential. But the basic premise is that, of course, you want to use modular invariance. So you want to relate the system at high and low temperatures, because what generically the CFT does, so the part of the CFT, just to stress that are generic, like what the Carty formula tells you is like, yes, there will be a regime up to here where it will look constant. And then there will be a regime, like, I don't know, to some point here, just to be random, where it will look like that Carty formula. Okay? So for a modular invariance, basically tells you about that this is always here, this is always here. And so the question is, we want the middle. And so the way that they proceed is basically by saying, let's split the spectrum to make it explicit between states that they will call light and states that they will call heavy. So they chop the partition function in two. Okay? So they define basically a parameter epsilon. So they will define what they call light as states that have energies that go between the vacuum, and some parameter epsilon that will be kind of small, but not quite zero. But OK, there will be some small parameter epsilon here, and then some heavy part of the spectrum. Well, heavy plus medium, but because then after the result is done, there is something that you should generally call heavy, but basically just for the purpose of now, states that are above this epsilon. Okay, so what's that? So this is part that you have to input depending on how strongly you want that phase transition. So it's right now I have said nothing about it, but as you try to basically what you want to do, so that the name of the game is the question was asked, how does epsilon scale with the system? At this stage, we haven't said anything, but this is where you have to be careful about the name of the game will be how well can I approximate the partition function by the light spectrum.
But I guess it has to go like 1 over L, right? That's the only scale in the model.
Sorry, what is L in your?
Just the radius. You set it to 2 pi, I guess. The radius of the circle.
Yeah, but it can also, we're taking C large, so epsilon can also scale with the central charge. Yeah. So it doesn't have, energies here don't have units in my conventions and this CFT conventions, but in general, like it could scale with the central charge of the theory. So, but one thing that was very beautiful that they proved, and this is where you can see like, okay, what happens to these approximations? So for instance, when beta is bigger than 2 pi, they can bound the logarithm of the partition function in this way. So this is just a general result. Here, you're not really assuming anything. So this is an inequality. So if the temperature is bigger than 2 pi, modular invariance and a series of tricks that I don't have time to do, but there's nothing detailed that you say about the theory. You basically can show that the partition function is bounded, of course, is bigger than just the light spectrum, but it's also bounded from above by this quantity. You can't. And I'm writing even bigger than you. Sorry, this part is important, so let me write it. Sorry, and beta prime here is the inverse, the modular, the S transform of beta. Sorry, I forgot to define that. Okay? Now, what's interesting about this formula is that you're bounding the partition function by something that doesn't really depend on the CFT. But at the same time, you have to be careful about this, that if you take beta close to beta prime, so if you take beta close to 2 pi, this means nothing, because this is infinity, right? So of course, if beta is very big, then you will have some choice of epsilon here, and it will tell you, you're bounding, this is a good bound. But if you put beta equal to beta prime, which is the point, it's 2 pi, the self-dual point, then you're only bounding it from below, but not from above. And so the name of the game is basically trying to see, like, OK, how useful is this bound, and how well, basically, can I approximate log of set by log of set light? That's the, so you want to feel that when you write down log of set, that you can say, this is the logarithm of the light contributions plus something of order 1. But this order 1 part, you do have to be careful that it's not a uniform. It's not always something that is controlled to be small. So this is where you do have to be careful about the approximations. And then here, the prime means that you're evaluating it at the self-dual point. And so that you have that behavior for the free energy. So that's one first statement, that there's a choice of epsilon as you take c going to infinity, for which that is true. And then I think I have how much? 3 minutes. OK. And so then the statement then, furthermore, then what you want to say next is that you want to say that the light spectrum is actually, furthermore, just controlled by the vacuum. So then the next step by the vacuum, so that you can have the approximation. So basically, you want this light part of the spectrum to just look like this. So log of set is basically the negative of these numbers. And the statement is that, so if you write down, so let me write down the partition function just for the light states. So this is just the states that go between epsilon. What they prove is that set L will basically be well approximated by C beta over 12 if the density of states is bounded dependence on epsilon. Okay? What's that? Sorry, log C. Yes. Thank you. So this is what we call the HKS bound. So the statement is that if your theory has a light spectrum that is bounded by Hagendorn growth, so here Hagendorn, I'm calling this Hagendorn because you have an exponential growth with a linear dependence on epsilon, on energy up here. If your spectrum is bounded by Hagendorn, then the light spectrum is bounded by Hagendorn, then you're going to have, you're going to basically extend the Carty regime. You're going to be able to say that that entropy actually, you can move it higher and higher up, depending on how light things get. But basically, you'll be able to go all the way up there. Okay? So it extends. So what HKS does is basically extend Carty for anything that has energies actually bigger than C/12. So if you're if your light spectrum, so light here, this is what I call, again, to reinforce, light states are bounded by Hagendorns, then you can confidently apply the Carty formula for states that have energy bigger than C/12. Okay? This does not cover the whole range of black holes, but that's fine, because actually from the canonical ensemble point of view, these black holes are canonically unstable. So it basically tells you that from here upwards, the black holes are dominating the ensemble, and then you can use the Carty formula to describe them. Okay? So this is our criteria. And what we're going to do in the last lecture is understand how stringent is that criteria. Can I start looking for CFTs that comply with it? And do I think that those theories have and meet my, I deleted my grand goal. And that basically would give me a theory of gravity that has a low energy description in terms of an EFT. So, okay, lunchtime.
All right, thank you. So before it is lunchtime, are there any more questions at this point?
This bond has any implication for the spectrum here that's happening?
We'll talk about that tomorrow. Let me leave you in suspense.
Any other questions?
They're all very depressed that pure gravity doesn't make sense. You're like, oh, maybe we don't have to do string theory. Sorry,
One more over here.
Yes, yeah. So so tomorrow I'll list more conditions. So this is just one. So you should just view this for now, because I decided to just revisit the Carty formula, right? So this is just one out of the things, and again, I erased it. Out of the things that I was listing as things that we were comfortable matching, then of course there's many more things, right? Even at the level of correlation functions, and this is where this comes in as well. Like you have to ask, okay, what are these conditions? What is the list of necessary conditions, and how should you phrase those necessary conditions in a way that can actually implement them? So yeah. So we'll talk tomorrow. Basically, we'll start the lecture by talking about, okay, what should I be demanding? And this is just to illustrate that even from the point of view of the very successful, very acclaimed Carty formula that you all guys were like happy to say, yes, it matches, and then we go home, you still have to input conditions if you want to claim that this is equal to that. Okay? It's not. So you want to do precision holography, not wishy-washy holography.
All right. With that sentiment, I think we'll end here. So let's thank Alejandra again. I will return at 2 p.m. for David Simmons-Duffin's last lecture.